Hello, in this video we're going to wrap up the final pieces of simple machines, which pretty much means a brief look at compound machines, or at least one of them, and then something on gears and gear systems, because that's closely related to the stuff that we've been looking at. So first of all, let's look at compound machines. I've pulled an example question out of a really good book that you can actually get for free online because it's so old. This is Fred Miller's book from, I think it's 1908 or something like that. Progressive Problems in Physics by Fred Miller. It's well worth having a look at. It just has loads of these questions. So I pulled out his first compound machine question. I mean, you can see we're up to question 672 here. He has a lot in this book. And it's interesting to see how these questions were written back in the day. It's also good at the back as well, because I think that's the book. I'm pretty certain it is, where they have entrance exam papers for Harvard and places like that from back in, over 100 years ago. So yeah, interesting stuff. Right, so what are they asking for here? They're talking about a hogshead of molasses. So a hogshead being a big barrel. I mean, you can look up how big it is, but you get a lot of pubs called the Hogshead and things like that, don't you? It's just a big barrel. We've got molasses, so lots, produced from sugar and such like. So we got a big barrel of stuff is essentially what we're getting at here. It's been rolled up a 20-foot gangplank of a steamboat, the deck of which is 6 foot lower than the wharf. Right, the rope, one end of which is tied around the top of the gangplank, runs down, passes under the barrel, and up to 2 men at the wharf at the head of the gangplank. What force must each man exert if the hogshead weighs 500 pounds? Okay, so let's get a sketch out on this. So we've got our gangplank. That's our first simple machine. We've got an inclined plane. We've got the barrel at the bottom, our hogshead, which needs to be raised through 6 foot. The length of the gangplank, they've told us, is 20 foot. So we're moving it through 20 foot. So we can already see there for our gangplank that we're going to be getting a mechanical advantage of 20 divided by 6. So that's the advantage that we're getting there on our inclined plane. Now we've got a rope as well, one end of which is tied. I'm going to put the rope in blue. So we've tied a rope at the top of the gangplank. It goes down and then under the barrel and then back up to these two guys who are standing at the top here, who are going to be pulling the hogshead up the ramp. So we've now got a pulley system going on here, because we're going to be putting an effort in here, which is going to double up because of the tension along the length of the rope. So we've got another mechanical advantage of 2 because of our pulley system. So we're going to combine these two mechanical advantages together in order to lift this hogshead. So here we've got 20 over 6, so 10 over 3. Then we're going to double that. We've got 20 over 3. So we've got 6 2/3 is our mechanical advantage. That's the overall mechanical advantage, the 6 over 2/3. We could leave it as 20 over 3, might be easier. So the force that we're going to need is we're going to need to divide our 500 pounds, because pounds being a weight, and it doesn't matter. You'll notice here that the units haven't come into this at all. We're going to divide that by 20 over 3. Providing you're using consistent units, it doesn't matter. For our inclined plane, we've cancelled the feet when we've divided 20 by 6. So it doesn't matter what we've measured them in, it's just the ratio. And it's the same that we're going to have here. Okay, they're saying it's 500 pounds, but again, we're just getting a ratio going on here. So we're going to divide by that. So we're going to get 1500 divided by 20, which is 1500 divided by 20, so 150 divided by 2, so 75 pounds of force we need to put in order to raise this hogshead up. So yeah, we're just combining mechanical advantages. That's all we're doing. You're multiplying them together, and that's what's happening in this compound effect. You just keep multiplying everything up, and you get bigger and bigger effects. So 75 pounds, lifting 75 pounds isn't really that much. You probably don't even need 2 people to do it. But I suppose it makes it a bit easier for them if you've got it split between the two. So that's an example of a compound machine. Now I'm going to have a quick look at gears, because this comes up quite a lot, and it's a useful thing to think about. So we've got basic stuff with gears. So say I'm going to draw them as circles. I'm not going to try and put all of the cogs on, but imagine that these are. So if I was drawing them all with these cogs on, it's just going to take ages if you've got all the teeth on the gears, and it's going to look stupid because I'm not going to be able to draw them very well. But you've got 2 cogs meshed together nicely like that. As we rotate this one round, maybe this is on some shaft, so you've got wheel and axle thing going on here. We rotate that one round, and then we've got a second gear here, maybe that's on another axle there. So say this one has got 40 teeth, this one's got 20 teeth. If we rotate this one once, we're going to have rotated that one twice. So if we had, we've rotated it twice, so we're going to have halved the force on this. So we're moving further, but we've got less force. And also you'll notice as this one's moving that way, in a clockwise direction, the gear attached to it is going to move in an anti-clockwise direction. So we got a number of things going on there. We've got a change in direction. We've got a change in the axis, that the forces have been moved somewhere else. So we're applying a force over here, and it's coming out over here. It's going in an opposite direction, and we've changed the magnitude. So in this case, going from big cog to little cog, we've reduced the force, and we've increased the distance. If we were going in the opposite direction, we would be increasing the force and reducing the distance. So it's the same sort of approach that we have in in all of our simple machines. We're still looking at that work in equals work out. Now you don't have to have the cogs directly touching each other. On a bike, things are going to be going on a chain. The advantage on the chain is if you drive around here, the chain's going to move that way, which is going to drive the other gear in the same direction, which is useful on something like a bike. So when you start pedaling, you don't go backwards. We're going to be driving the wheel in the same direction. And you'll see at the back of the bikes, you have these big, these collections of different gears. So all of the cogs are different sizes. And we're going to have the same thing going on with all of this. That if you're on the big gear, then you're going to be moving slower, but it's easier. If you're on the small gear, then you're going to be moving faster, but it's harder. So we're just changing that ratio between the two exactly in the same way. You got a similar setup, but slightly more complicated when it comes to cars. So the setup you have on cars is you get we've got the engine. I mean, the reason you have gears on cars is because we want to try and keep the engine operating at a sort of optimal number of revs. So you've got an axle coming out of the engine, which has got a particular cog attached to it. And typically for a car, for optimal working of the engine, you want to be keeping around about 1500 to 2000 RPM. So you want that number of revs per minute. If you go below that, you're not really getting the power out. If you're going above it, then you're just knackering out the engine, and you're just going to wear out all of the parts. So we're trying to keep this going roughly at the same sort of number of revs. So having gears means we don't have to change the revs of the engine. We can keep that as constant as possible. and we can attach this in a variety of gears. So you have another gear, a cog, which is attached to that, more or less often in a one-to-one relationship, one-to-one ratio. This goes off to another shaft, which has then got a collection of gears of increasing size. So say you got a 5-gear car, each one of these is going to be getting bigger as you go along, and well, you have another one at the end as well for reverse, which would be sort of a mid-size, maybe slightly smaller one. And then you get a second shaft, which is the one that the wheel is attached to. So this goes off to the wheel, which of course is given a multiplier in itself, because you've got this big diameter on the wheel compared to the axle that's rotating. But then on here, you've got a set of gears which are decreasing in size. So these are meshing in. I'm drawing them slightly wonky here. They're meant to be centered on the on the axle, but these ones are decreasing in size. So we've got a set of cogs here which are getting bigger. We've got a set of cogs here that are getting smaller. Your gear stick will then come in and it will be deciding which pair of these are going to interlock. So if you're in first gear, then moving the gear stick to first gear will make these two gears interlock with each other. And then that'll be the one that's driving the wheel. So it's creating this chain there. It goes from the engine to this cog, and then whichever pair are connected to each other. So in this case, first gear, that one and that one, which then drives the wheel round. So as we change gear, we're just deciding which pair of these are going to match up. And of course, you're getting a different ratio on each one of these. So in first gear, you're driving a really big wheel, a big gear on the wheel shaft. So if we're driving that big gear, we're not moving as far, but we're able to put a lot of power through it. So that's why first gear is good for going up hills, because you're not moving quickly, but you're putting a lot of power through it, so you can lift the car up the hill. If you've gone all the way over to fifth gear here, then you've got a much smaller cog at the end of this chain. And that means that we're going to be moving a long way, but with lower power. So if you've already got up to speed, and you want to be nipping along at 70 on the motorway, then yeah, you put it into that gear because you don't need the power. You're just maintaining high speed. You want to go a long way. So that allows us to travel further. And all of this can be done without getting outside of this rev range, which is optimal for the engine. If you didn't have gears, then you've either got a very limited speed that you can go at, range of speeds is not that great, or you've got to keep changing the revs, which, as I said before, means you either don't get the power if you go to low revs, or you wear out the engine too quickly. So yeah, you've got a lot of things going on. I mean, with the reverse one, you might get an intermediate cog on these to make it match up, because they sort of sit in between the sizes of these cogs. They don't sit quite as comfortably in the sequence, so you can have this intermediate one called an idler cog, because it's not really doing anything, it's just there to connect up the two on the other side. So that means we can stick the reverse one at the end rather than having it, stuck somewhere inconvenient. So that's what's going on with all of these gear mechanisms. So you can either, we looked here at meshing them directly to each other, just a simple pair of gears you've got with a chain, and then you've got this more complicated gear system that you get in a car with with multiple axles and multiple combinations there of gears. So that's just an overview of the sort of things you can move into when you get into more complicated setups for compound machines and for gear systems. But it's worth poking around on this a little bit more. I'd recommend, maybe I'll put some more links again on this to stuff on gear systems. It's worth poking around on these and doing some calculations on the gear ratios and things. And if you can find an old car or someone who maintains classic cars, and you can start looking into the gearboxes and things, because that was what was so great about the old cars. You could tinker around and see all of this happening, whereas a lot of it's hidden away now. It's much harder to see in the newer models. Um, but yeah, if you do know someone who keeps classic cars, they would love to talk you through all of this sort of thing, because this would be stuff that they'll actually be working on in the garage. So you might be able to get a peek inside the gearbox and see how it's all put together.